Good morning, everyone. This video is about a complete question paper discussion. Complete question paper discussion. This is 12th chemistry, model paper 1, model paper 1, which I received this 2021 year. Okay. So here we go. This is about. I will discuss each and every question in a detailed way. So one by one. So please follow that, and then hope this is really helpful for your examinations. So here we go. This is how the first question. This I received from some of my students. So the question I answered these things in random. So all the questions in the question paper I'll be discussing. So but in random way. This is the first question. The first order reaction. First order reaction takes 20 minutes for 25% completion. For 25% decomposition. Calculate the time when 75% of the reaction, 75% of the reaction will be completed. Will be completed. Will be completed. This is the question number 1. So how do we solve this problem? And now you see that in 20 minutes, it took a time of 20 minutes for the 25% decomposition. So the major formula what you have to know is the rate constant K is equal to 2.303 divided by T log of A by A minus X. So what is A into A minus X? A is the initial amount. And X is the amount decomposed. Or you can say that X is the amount of product formed. Okay. Amount of product formed, and that is actually 25% of the initial concentration, that is A. So we can write that A, 25% of A. This is what is given us. And now A minus X will be amount left. After decomposition or after X amount decomposed. Okay, amount left after some reaction. Okay, amount left after, you can say after some reaction where the X is decomposed. Okay, where the X is decomposed. Like this you can think of. Now I hope you are all clear about this. And now here, this we have to apply this, and now you can make a note by pausing the video up to here, and then I will clear it from here. Hopefully you would have written. Okay, we'll clear it. And now here we go that this we'll use this formula. T is equal to 2.303 divided by K log of A by A minus X. So here they have given the X is 25% of it. So A minus X will be definitely 75% of A. This is how we can calculate A minus X will be 75% of A. So we can write T is equal to 2.303. This is for 25% decomposition. So T 25% will put T 2.303 divided by K log of A by 75% of A. 75% of A. So when you plug in the things, you get the A minus quantity is 70% of A that we have plugged in. So 1 by 70% is 3/4, so it becomes 4 by 3. So you have 2.303 by K log of 4 by 3. This quantity they have given, and they have given that T 25% is about 20. Okay, right? So you have the T 25% is about 20. So we will plug in this 20 here. That is 2.303 divided by K log of 4 by 3. That's what you have. And now T 75% we can find. Similarly, T 75% will be like you have 2.303 divided by K, and you have log of this one A by A minus X once again. Now for 75% A minus X will become, now for 75% decomposition, X is 75% you can put, and the A minus X part becomes 25% of A. Okay, so this becomes 25%. So that's 25% of A. So once you substitute, you get log 4 here. So this T 75% becomes 2.303 divided by K. You get log 4. So you can note it up to this point, and then simply we can take the ratio of these two to get the required value. So I will take the ratio of this by this, so to get the values. So I'll clear it off. So we have, I can clear it. So I hope I can clear. So here we go. So okay, I need this. So we'll do that. Okay, noted. I hope noted. Fine. So when you take T 75% divided by T 25%, you will end up with like 2.303 divided by K log 4 is on the top, whole divided by 2.303 divided by K log of 4 by 3. This is how you get like that. Now 2.03 by K is out, and then T25 is 20 minutes, you know that. So T75% will become that T25% into the log 4 divided by log 4 minus log 3, we can write. And in the question, they have given the values of the log 4 to the base 10. That's about 0.6021, 0.6021, and here the values are to the base 10 only, and log 3 to the base 10 is about they have given it as 0.4771. 0.4771. So these values are provided to you. So once you plug in the values, you are going to get this. This is 20 minutes. That is T25% is 20 minutes. And the log 4 value is about 0.6021 whole divided by 0.6021 minus 0.4771. So once you plug in and then give the calculation, this works out to be around, I got this around 96.34 minutes. Okay, this value works out to be 96.34 minutes. This is the value I got. Okay, 96.34 minutes. This is the value I have obtained. Okay, clear. Now let's move on to the next question. I hope you would have written this and then understood this question, how to handle this. Fine. let's go to the next one. Question number 2. For a first order reaction, I am answering the choice questions also. For the first order, you will all get benefited. For the first order reaction, show that the time required, so that the time required for 99% of completion, for 99% of completion, for 99% of completion is twice the time required, twice the time required for completion of 90% of the reaction. 90% of the reaction. So let's solve this. This is also of the same kind for the first order reaction. They said the basic formula is like this: T is equal to 2.303 divided by K log of A by A minus X. This is how to start with. And now it's given that in the case 1, it's X is about 99% of A. That's what it is. And your A minus X factor works out to be like A minus that 19%. A minus that becomes 0.99 of A. So that's what happens. So the A minus X happens to be just 1%. Okay, 1% of A. So that's what happens. So this is just 1%. A minus X happens to be 1%. And now 1% means, please understand that is 0.0001 is what we get. So 0.01 A is what you have to see. So that's 1% is remaining. So let's calculate for the 99%. The 99% happens to be 2.303 divided by A. So log of A by 1% of A. So you have 1% of A, 1% is 0.01 times A. So this happens to be 2.303 divided by A log the A gets cancelled, 1 by 1%, that is about 100. Okay. So 1, that is 10 power minus 2. So this becomes 100. So this one is 2.303 divided by K log of 10 square is what you get. What I did was 1 by 0.01 is it. That is 1 by 10 power minus 2. That is about 10 square, which is 100. This is what I have done here. So for this, I applied the log. So you get, so after you can note that this happens to log 10 square is 2. So 2 into 2.303 divided by 3. Let's leave like this. Okay. So pause the video and then make a note. I have got this T99% as 2 into 2.303 divided by K. This is what I got for 19%. And now for 90%, I got to calculate. That is like 2.303 divided by K. So log of, you have A divided by, this time X is about 90% it has dissociated. So your A minus X factor works out to be 10% of A. So here I put 10% of A. So A once again cancelled, 1 by 10%. So 10% is actually 0.1, right? So 1 by 0.1 is 1 by 0.1 is what I get. That is about 10. So that factor works out to be, so T 90%, 90% if I work out. So it happens to be 2.303 divided by K. I get log 10. The log 10 to the base 10, that value is 1 anyway. So you have this one works out to be 2.03 divided by K. So you have this, and then we'll consider the ratio. So T 99% divided by T 90% is what you get. That's over like 2 into 2.303 divided by K, whole divided by 2.303 divided by K. So the 2.303 is factored work out. So that's cancelled all over. So you get T 99% is double that of T 90% for the first order reaction and so. So this is how you can handle this question. Hopefully you all understood how to do that. So if you have any queries, you can always put it in the comment section after watching the video. There is no issues on that. Now, let's clear this and then go on to the third question. The question number 3. Name the element. Name the element in the 3D and why it does so. Why it does so. So that is the one question. The answer goes to be like this. So the answer is manganese that has the largest number of oxidation states. That is the element which is having the largest number of oxidation states, and it has the oxidation states of about +3, +4, +5, +6, and +7. These are the oxidation states it has. And now this the transition elements, a general answer you can give like the transition elements show variable oxidation states. So manganese is a transition element, so you can give a general answer. So variable oxidation states, due to the participation of Ns and N-1 d electrons in bonding. So this is the reason why the transition elements show variable oxidation states. So let's move on to the next question. Hopefully you would have written this. So you can pause the video. If you're not noted, you can pause the video and then make a note. We'll move on to the next one. Question number 4. Out of Cr3 plus Mn3 plus, which is stronger oxidation? Which is stronger oxidizing agent? Stronger oxidizing agent. And why? See, oxidizing agent means this thing, whatever is given, that has to get reduced, and then what is the chance that these two gets reduced is what we need to see. So when you see the so when you consider the chromium and the manganese, okay, you have You can write the thing that Mn3 plus, okay, Mn3 plus is stronger oxidizing agent, okay. Stronger oxidizing agent because it has because it has 4 electrons in its because it has 4 electrons in its valence shell. If it picks up and when it gains when it gains one more electron and when it gains one more electron to form Mn2 plus to form Mn2 plus it results it results in half-filled orbital d5 configuration which leads to extra stability which leads to extra stability so this is the thing. So when you see the chromium 3 plus and then manganese 3 plus, if you check in the electronic configuration, so the manganese and chromium, so the chromium 3 plus will be having the argon 3d3 4s0, and now this one will be like manganese 3 plus will be argon 3d4 4s0. And now the thing is oxidation means the as I told you, this agent, whatever you consider, it should be able to pick up the electrons. Which one is having more ability to pick up the electrons is what you got to see. And now manganese 3 plus is having more ability compared to the chromium 3 plus. The reason being when the manganese 3 plus picks up the electron. So the manganese 3 plus it picks up the electron, so it forms Mn2 plus. So when I take Mn2 plus, it has the configuration argon. You have 3d5 and then 4s0. See the 3d5 configuration when you are going to get the 3d5 configuration, that is the half-filled orbitals. So when you are going to get the half-filled orbitals and then this kind of configurations, that leads to extra stability. So that's the reason this process will happen really quick, and then this is prone to happen when compared to the chromium 3 plus. So that's the reason they are very good oxidation agents. So oxidation means removal of electron. So these agents can remove the electron so easily. So that's the reason. That's the answer for you. So you can make a move. Let's move on to the fifth question. Question number 5. Write the IUPAC name of complex CrNH3 twice Cl2En. So this is what you have, and the Cl, this is what you have. Now, what to write the name, and the first part of the question first part, and now the second part of the question. You got to write the formula. Write the formula of compound Write the formula of the compound. Potassium, potassium, tetrahydroxo, tetra, tetrahydroxo zincate 2. Zincate 2. This is the thing what we had to write. So for this, the answer, the first one is diamine dichloride, dichloride. This is the first one, diamine dichloride, ethylene diamine, ethylene diamine, ethylene diamine, chromium chloride. Chromium, the oxidation state is 3. So chromium 3 chloride. So this is how you get the mean one. The second one is the compound we had to write. So that is potassium tetrahydroxo zincate. So that is K2Zn OH 4 times. This is what you get. So these are the answers, the first and second. Okay. Now let's move on to the next. Here I don't have a place. That's why we had to write the name in such a way that there is no gap. So I hope the rules you know. Right. So here we go. This next one, question number 6. So arrange the following. Arrange the following in the order of displacement. Displacement in SN2 reaction. So this is the question. So the first one is 2-bromo 2-methyl butane, 2-bromo 2-methyl butane, and 1-bromo 1-bromo pentane, and the third one is 2-bromo pentane. So these are the things which is given. So this is the first part. So the and now this the so 2-bromo 2-methyl butane. So if I write the structures of so let me call this as the first one. First one is having the structure is like this. So you have this is 2-bromo 2-methyl butane, and then the second one is 1-bromo pentane. 1, 2, 3, 4, 5, and then this is 1-bromo pentane, and that's the third one will be like 2-bromo pentane. So this is like this. 1, 2, 3, 4, 5, and then here at this position you have to go. Always that the SN2 reaction is preferred at the primary alkyl halides, they will undergo the SN2. So second is 1-bromo pentane, that's greater than the secondary one. So the secondary one is third. That is secondary alkyl halide. Primary alkyl halides, this is the order. Primary greater than secondary, greater than tertiary. This is the order. If you follow, then you are done. So the primary, this is the primary alkyl halide. This is secondary. So 1 greater than 3, greater than 1. This is the tertiary alkyl halide. So this is the one. So second, third, and one. This is the order it will follow. So hope you got. And now we will solve similar kind of question this which has come in the choice. Another question is there in choice, same kind of question that also will solve. So make a note. So another question, seventh one. So what I have given is, so order of reactivity towards SN2 is what they have given. So the first one here you have to find order, and 1 bromo 3 methyl butane, 1 bromo 3 methyl butane is the first one. Second one is 2 bromo 2 methyl butane, 2 bromo 2 methyl butane, and the third one that is given it as 2 bromo 3 methyl butane, 2 bromo 3 methyl butane. So let's draw the structures of this one. So first let's plug in the butane chain. This is how 1, 2, 3, 4. That's the butane chain. And in the primary position you have bromine, and at the third position, that is 1, 2, 3. At the third position you have methyl. So that is the first one. Okay. And the next one is like 2 bromo 2 methyl butane. So you have at the second position itself you have the methyl as well as bromine here. So here this is a primary one. Okay, this is the tertiary one, and you have 2 bromo 3 methyl butane. So here we go 1, 2, 3, 4, and then that at the second position you have the bromo, and then in the third position, and here you go. This is the secondary one. Okay. So order of SN2 primary greater than secondary greater than tertiary. You can follow that, and then I hope you can do this. So here it comes out to be 1. Otherwise, this is the highly reactive one, greater than the 3, yeah, greater than 2. So this is the order in which it will decrease. This is the decreasing order. This is the decreasing order. So if they ask you to write the increasing order, just reverse this. So that's 2 less than 3 less than 1. So that's how you can give. This is the increasing order. Whichever is asked, you can do that. So from the structures, it always follows this one. Please follow this one. Primary greater than secondary greater than tertiary is for the SN2 reaction. So here it follows that that's a primary alkyl halide, secondary alkyl halide in greater than tertiary. Primary greater than secondary greater than tertiary. That's the idea with which we are following in order to solve this particular problem. Hope it is done. I hope it's clear. And now this is a choice question. Also, I am solving. Now we'll go to the next one. So I am separating all the questions into pieces, and then I'm answering one by one. So here we go. So in the following halogen compounds, which one would undergo? Which one would undergo SN2 reaction faster and why? So this was the question, and here it's given this CH2Cl, and this one. So under the same logic, you had to solve this, and you see this is a primary alkyl halide, and this one you can see this is secondary alkyl halide. So out of these two, we'll call it as structure A, structure B. Structure A will react faster than the structure B. So that's the answer in the case 1. And they have given the case 2. There is a case 2 within the question. So why structure 1 reacts faster? That is because the primary alkyl halide is more reactive compared to secondary alkyl halide in the case of SN2 type reactions. The next one is like you have this one which is given, and the same kind of structure, and you have chlorine, and you have this is like structure A and structure B. Both are primary, but in this case, like iodine is a very good leaving group. Iodide is a good leaving group. I minus is good leaving group. Good leaving group compared to Cl minus. Hence, in this case, A reacts faster than the dot. Okay, structure A, that molecule A reacts faster than the dot B. So hence the answer for these two. Okay, hopefully you have written, and we'll add some more points over here in the last one. Iodide is a better leaving group, compared to Cl minus. Iodide is a better leaving group compared to Cl minus, as it is of larger size. It will be released out. At a faster rate. In presence of a nucleophile. So that's how you can give the answer. So this is the extra point you can add, and then you can impress the examiners by adding these points. Okay, let's do one more question. Let's move on. The next one is the 8th question. Complete the conversions. In less than 2 steps. The first one is ethanol to propene nitrate. So first write ethanol. So here we do the conversion. Here itself I'll write. So ethanol is C2H5OH. And then we'll treat with SOCl2 pyridine. So this is the best way of converting the alcohol to alkyl halide. So we use C2H5Cl, we get. And then let's treat this with something like KCl. So you get C2H5CN, which is our propene-nitrile, propane, sorry, propane-nitrile is what is given. I have written wrongly. It's propane-nitrile. So this is the conversion. Okay. Now let's do the next one is aniline to fluorobenzene. Aniline to fluorobenzene. Here we use Sandmeier's reaction. So aniline we take aniline and we treat with NaNO2 HCl, and then between 4 degrees, so between 0 degrees centigrade to 4 degrees centigrade, when you do this, and you will end up with benzene disonium chloride. So that is N2 plus Cl minus. So you treat with CuCl, then and then you have this chlorine on the top, right? That's what you get, chlorine. So you would have written the answer hopefully. Now let's move on. You can pause the video if you're not written, and then we'll move on to the next question. That is question number 9. Next one. Give reasons. Give reasons. So this the first one is aryl halides. Aryl halides are aryl halides are extremely less reactive. Aryl halides are extremely less reactive towards nucleophilic substitution. Towards nucleophilic substitution. Towards nucleophilic substitution. So why it is so, that we had explained. The second one is this SN1 reactions. SN1 reactions are accompanied by racemization by racemization in optically active alkyl halides. Okay, so this is the things I have to remember. Now the first one can be answered like this. So this is you can say that the first one, the partial double bond character of CX bond uh, in aryl halides. Okay, in aryl halides. So this is how the reason you can give. So here, and the next one is that electron withdrawing groups will increase the reactivity, will increase the reactivity will increase the reactivity of nucleophile substitution reactions of nucleophilic substitution reactions. When they are present, they should be present at the ortho and para positions. So that's how. So the double bond character, let's discuss the double bond character. Double bond character comes because, so you can see this, the lone pair of electrons on the alkyl halide will participate in the resonance. So that's the reason you can write the equivalent structures like this, what I'm doing. So here double bond here plus, and now the charge will shift like this, so which creates a kind of dipole sort of thing. Okay. Now these are the charge shifts you can do, and this is the resonance structures. You want to draw the resonance structures and show this. That could be much better. You had to pick a right answer for this. So these resonance structures will show that this is the reason why it's extremely difficult. That is one reason. The other one is the bulk phenyl group. Okay, this phenyl group. Okay, so when you do that, you will get this back. Okay, you will get this back structure. The structure you will get back. And now this is the another reason you can write is that bulk phenyl group will hinder in the attack of nucleophile. Attack of nucleophile. These are the reasons you can write, and then along with the resonance structures. Okay, I think I missed one structure over here. So let me draw that one also so that we have a look at it. So here we go. Here we go. Here plus. Now it's like this. And now this comes out to be the final structure. So this gives both the Kekule structures. Okay, you have to rotate between the both the Kekule structures of benzene. So here you go. Both the Kekule structures of benzene here. So this is how you get the resonance structures, and this is how you solve. Okay. Now, oh, it's fine. That's the first one. You can give the answer. The second one, second part of the question, part two of the question, is like this. So another reasons you can attribute to for the lack of reactivity is that the one part is next is phenyl cations. Phenyl cations are highly unstable or highly unstable. Highly unstable. So I'll discuss the second part of the question. This is within the first part itself. Highly unstable, thus making SN1 reactions difficult. Thus making the SN1 reactions difficult. The next one is that because of the double bond character of CX bond, it is shorter compared to normal sp3 carbon X bond. Okay. Here we see that the CX bond is sp2 carbon X bond. Okay. Because benzene in the all the carbons are sp2 hybridized. So this sp2 X bond is like slightly shorter compared to that of the normal sp3 X bond. So this is another reason what you can write. Okay. So these are the things on which the part one question you can answer. So the next part of the question is about what are the things they ask is that now why do you end up with the part two is ethanol reactions is will give racemization. Why do we end up with the racemization is what we have to answer. The second part is that the carbocation, you can answer like this, the carbocation is having a planar structure, is having a planar structure, carbocation is having a planar structure. The planar carbocation, the planar carbocation can be attacked by nucleophile from both sides. So this I'll illustrate here with the figure. So it goes like this. You have CH3 C plus. So it's like this you have. And now this you can put it like in a one frame kind of thing. So here we go. So see, I'll take a tertiary carbocation so that you will understand much better. So this is the tertiary carbocation. So tertiary carbocations will undergo SN1. So here the attack of the nucleophile can be from this side or as well as from this side. So this nucleophilic attack can happen from any side. So you get the configuration, once configuration, you get retention, you get inverted. Both the things are possible. So the reason you get the racemic mixture. Okay. So it's 50% chance from this side as well as you have 50% chance from this side. So both the front and back attacks are equally possible. So you from both sides, so equally possible. So equal possibility of forming DL isomers. Okay, D and L isomers. DL isomers. So you know what is DL refers to dextro and levo rotatory. So DL isomers in equal proportion. Equal proportions. So this is what. So when the DL isomers are of same proportion, it's called racemic mixture. Racemic mixtures will have. So let me clear this point. This one. DL isomers. Racemic mixtures will have DL isomers in equal proportions. Okay, in equal proportions. If there are equal proportions, it's optically inactive. This mixture is optically inactive. You can tell. This mixtures will have DL isomers in the same proportion, and hence they are optically inactive. Hence you, so up to here you can pause the video and note. So hence, even we start with an optically active alkyl halide. If at all, when it undergoes SN1 reaction, we end up with a racemic mixture. We end up with racemic mixture, or sometimes it's also called racemic modification. So here, that's the answer for this. So let's move on to the next one. The question number 10. The unit cell of an element of atomic rate mass of 108 U, 108 gram mole inverse. Okay, you can take like this instead of U, and density 10.5 gram per cc is a cube with an edge length of 409 meters. Find the type of unit cell. Find the type of unit cell. Find the type of unit cell of the crystal. And what is given is the value of Na, that is 6.023 into 10 power 23. This is given to us. So that is mole inverse. This will be the units of the Avogadro constant. And now we have to solve this. So the straight away formula, what you can do is that D is equal to Zm by A cube Na. So where Z is the number of atoms per unit cell. So if I find that Z, then I can find what is the type of unit cell. So for the to know the type of unit cell, so if it is like BCC, you will get Z equal to 2, and the primitive means simple cubic type. Simple cubic type, you get Z equal to 1, and you have the FCC type. you get Z is equal to 4. That's it. So okay, now let's check that what is the value of integrate. So it is D is the density. So D into A cube into Na whole divided by M is what we have to put. Plug in the values, that's all you have to do. Z is equal to D is you got 108 gram, sorry, 10.5 gram per cc, 10.5 gram per cc. So a cube that is 494 meters, that's 409 into 10 to the power of minus 10 you can put. So that will be in centimeters. So that's whole cube. So Na is 6.023 into 10 power 23. So next one is the molar mass. Molar mass you can put like 108 gram mole inverse. So when you plug in these things, so you will end up with an answer which is close to 4. Okay, 4.0063 around like this. So you can take it like 4. So I got the value Z is 4. Z is 4 means FCC. Here you can mark it. So this is where you have this is how to solve the question. So you can try using the calculator and then get it done. So hence you got Z equal to 4, which refers to the unit cell Z is equal to 4. This is what you have to remember. Z is equal to 4. The unit cell is FCC. And Z is equal to 2. That is a 2 atoms per Z equal to 4 means refers to 4 atoms per unit cell. Okay. And now Z is equal to 2 means that that unit cell is BCC, which is 2 atoms per unit cell. And if you have simple cubic, Z equal to 1 means you have simple cubic. So that is 1 atom per unit cell. So these are the facts which you have to remember. So a little bit of things, and then we should draw this. Okay, we'll understand it much better. So we'll draw what is and FCC, so that we'll all have the complete detailed idea about what is FCC. So I try to draw this. So here you go, and this is how. So I'm drawing a cube. So I will show from simple cubic to FCC all the way. So the thing is that the simple cubic is a situation where I will put up with different colors so that you can understand. So if I put all the corners of the cube are filled, the corner will have a contribution of 1/8. So 8 corners, each of contribution of 1/8. So you get 8 into 1 by 8, that is equal to 1. This is the case of simple cubic. And now when you go to the BCC, one atom will come at the center. So this is how within this same structure I can show you. So this is how you get the BCC. So inside atom will be counted as 1. And these 8 atoms will give a contribution of 1. So that is 8 into 1. So this happens to be 8 into 1, 8 plus 1. So this is what you get. So which works out to be 2. This is the Z value. And now in the case of FCC, so the atoms will come in the 6 spaces. The phase contribution. So this, if you assume this one not this space and this one and this space, Okay, so this one at this space and this one at this space. And then let's remove this at the center and then put it at the face. Okay, so when I put that in this space, okay, fine. This one in this space, okay, and now that's FCC for you. This is how you get the FCC. In FCC, there are six spaces. Six spaces will generate a contribution of yeah, this generate a contribution of 6 times half, and E space center will generate a half contribution, and now the 8 corners will generate 8 into 1/8 contribution, so which works out to be 4. So you can see this is 2 3s, and this is 1. 3 plus 1 is 4. So that's how you get 4 atoms per unit cell. So this is the idea behind. So all of you, I hope you need to have this idea in order to solve this problems. Okay. Now let's clear this off. Now let's see the next question. Next question, I think it's the 11th one. Yeah. Explain the atomic radii. Explain the atomic radii of metals. Atomic radii of metals. Explain the atomic radii of metals of third that is 5D series, third series of transition elements. Or virtually explain this. The atomic radii of metals of third series of transition metals. Third series refers to 5D series of transition metals, or virtually the same as those of corresponding members of second, that is OB transition series. So this we had explained why it is like why the atomic radii of the metals of, so you can, instead of explain, you can say why this is so, why this is so. So why the atomic radii of the metals of third transition series? Okay, the third transition series refers to 5D series of transition elements are virtually the same, almost they are very much same as those of the corresponding members of the second transition series. So why this reason is, this is due to filling of this is due to filling of 4f orbitals. 4f orbitals and poor shielding effect of f orbitals, and poor shielding effect of f orbitals. Poor shielding effect of f orbitals. And you can say this lanthanide contraction is the answer with which you can do. Okay. So, for example, if you consider like 40 zirconium, 40 zirconium, and you have 72 hafnium. So, actually speaking, the titanium, zirconium, hafnium, they belong to the same group. Okay. Titanium, zirconium, hafnium will belong to the same group. So, you see the zirconium, hafnium. So, the atomic radii of zirconium and hafnium are nearly same. Zirconium and hafnium atomic radii are nearly same. Okay. So you can make a note of this one. So it is, so finally the question can be like they can ask you like zirconium and hafnium, why do they have nearly same atomic radii? This is like you can give lanthanoid contraction, and you can say that two shielding of the f orbitals, f orbitals. So these are the reasons you can give why that there is a size contraction. Okay. So co-shielding of f orbitals, it reduces the, you can say the what is the effect of this is that it reduces the size of the atoms. Okay. Reduces the atomic radii as due to the increase in the effective nuclear charge. On the outermost orbitals, which is attributed to the co-shielding of the orbitals. Co-shielding of f orbitals. Okay, this is how we can generate the co-shielding of the f orbitals. Is what is exactly what is happening is because of the co-shielding of the f orbitals, it reduces the atomic radii. This is due to increase in the effective nuclear charge on the outermost orbitals. Why the effective nuclear charge increases is because of the co-shielding of the f orbitals. This is the reason there is an increase in the effective nuclear charge. If the effective nuclear charge increases, the size will shrink. So, effective nuclear charge means increases, size of atom will shrink. So the radii automatically will come down if the size of atom shrinks. So this is the concept which you have to keep in mind while answering this question. Hope you got it. So they nearly, why is zirconium hafnium nearly having the same radii? So that's how another question can be posed like this. This answer wise they are same. Okay, I hope you got the answer. This is how if you respond you'll get the full marks. Okay, right. And let's go. Let's move on. The next one, the E0 values. The E0 values of Mn3 plus to Mn2 plus couple is more than that of for CR3 plus to CR2 plus. Okay, couple. Everything is shown in terms of the reductions. Okay, couple. Or you can think of this one also, Fe3 plus to Fe2 plus couple. So why it is so? This is what why we had answered. Why the E naught values of M2 plus. Okay. So when you consider this happening, it's like, let's say, it says that this is a very good oxidant, right? Mn3 plus. It says that the E naught values of higher. See, understand this one. E naught value increases. That refers to the delta G value that is equal to minus NF E naught. If I write delta G naught, this is minus NF E naught. That becomes more negative. E naught is more positive, which means that delta G naught will become more negative. Okay, more negative. So based on this funda, the reaction is spontaneous. So from this we can also say that the manganese 3 plus picks up the electron to give manganese 2 plus as a spontaneous reaction. And then it's a very good oxidant. So very good oxidant. So that's what the conclusion. You can make a conclusion out of this. I think we answered this one. The thing is that when the Mn3 plus gains the electron, okay, I will write it here. So you can pause the video and note down these things. So you can say that when Mn3 plus picks up an electron to become Mn2 plus, Mn2 plus is having the D5, 3D5 for a 0 configuration. And hence it is attaining a configuration of half-filled orbitals, which gives extra stability. Stability to Mn2 plus ion. Hence, the E naught values, okay, E naught Mn3 plus to 2 plus is greater than the top, even if you take. So you can check the chromium 3 plus to 2 plus transition, or you can check the iron 3 plus to 2 plus transitions, right? So you won't get the half-filled configurations when this is happening. Okay, so this in the chromium, if you consider this chromium 3 plus plus electron gives chromium 2 plus, the transition happens from 3D3 to 3D4. This is what happens in the case of chromium 3 plus. Or if you consider the iron 3 plus to iron 2 plus transition, so the electron configuration changes from 3D5 to 3D6. So this is what happens. So these are not preferred things. Okay. Now you need it's not like preferred or something. This extra stability is gained when you have this this kind of configuration 3d5. So d5 configuration, that is top-filled orbitals, that leads to extra stability for the particular ion of interest what we consider. Okay. Now, so these are the things what you have to know. So because this resultant configurations like the 3d4 and 3d6 in the case of the chromium 2 plus or iron 2 plus, these are relatively unstable. Okay, these are relatively unstable, not leading to D5 configuration. Okay, configuration or a D10 configuration. Both of us them are not happening. So the reason the E0 values are lower. So E0, so you can say that E0 values are lower, okay, for these things. Now lower for, I hope you understand this, iron 3 plus to 2 plus transition, or you consider the chromium 3 plus to 2 plus transition. So this is what you have to keep in mind. Now let's move on to the next question. Next question is repeat. The highest, explain why the highest oxidation state of metal is exhibited in its oxide or chloride. In its oxide or chloride. Why it is so? So if you consider the oxygen is having electronegativity scale wise, it's about 3.44, as well as when you consider fluorine, as per the Pauling scale, it will be around 3.98. So these are the electronegativity values of the oxygen and fluorine. So I'm talking about the electronegativity values of oxygen and fluorine. Okay. And now if you consider the group 16, so the group 16 is oxygen, sulfur, selenium, tellurium, right? So electronegativity decreases down the group. Okay. So even if I consider the situation of the halogens, that is group 17, the situation is same. So I get urine, fluorine, bromine, iodine. The electronegativity decreases down the group. So both in these cases, electronegativity decreases down the group. It's fact that down the group, the electronegativity decreases. So on top, you have oxygen and fluorine. This having a very high electronegativity. So which means that large tendency to form negative ion. Large tendency to form negative ion. That's what electronegativity means. Okay. Large tendency to form negative ion. That's what electronegativity means. Okay. So since they have very large tendency, okay, you can make a note of this one. Hopefully you would have written this. You can pause the video if you are not noted. Okay. Now so when you consider the oxide or fluoride, since they have very large tendency to form negative ion, they are very strong. they oxygen, if I write oxygen or fluorine, they are, so I can write, they are very, they are very good oxidizing agents. Oxidizing agents. So oxygen and fluorine, they're very good oxidizing agents. It's one thing. Hence, the oxidation state of metal increases when it's when it is combined either with oxygen or fluorine, whether with oxygen or fluorine. That's what happens. So, another reasons what you can write is that both oxide ion and fluoride ion, fluoride ion are highly electronegative. Electronegative. And have very small size. Have very small size. So these are the reasons why. So these are the properties which makes the metal makes the metal which makes the metal to raise for larger oxidation states. So this is how one can give the answer of this question. Okay. So let's move on to the next question. You can make a note of it. So let's start up with the new question. This is the part 2 of the question paper. Part 2, first question. Compare the complexes. Compare the complexes. Compare the complexes with respect to structural shapes, of units of units magnetic behavior and hybrid orbitals involved in the units. Hybrid orbitals involved in the units. So the first one is NiCl4 2 minus ion. And the case 2 is that NiCN4 2 minus ion. So these two cases we have to discuss about the magnetic properties and so. So let's understand. So please note the question. Once if you can pause the video and then you can note the question. And pause the video and note the question. Now, what I tell you is that, so I'll clear it. So here, when I consider the NiCl4 2 minus, here the nickel 2 plus is oxidation state, and nickel 2 plus will have a configuration of 3D8 4s0. The Cl minus is a weak field ligand. Okay, so the thing what happens is that this is the what you get is the 3D8 configuration. I will draw the 3D8 configuration 1, 2, 3, 4, 5, and this is how you have the 3D8 configuration. And now followed by 4s0, and 4s0 means no electrons out there, and then this is the 4p, and that's 4p for you. Okay, right. And now this 4s and 4p, they can combine to give you sp3 hybrid orbitals. And since the Cl minus is a weak field ligand, the electrons will not get paired here. The electrons will not get paired here. Okay, paired. So this is what happens. This is weak field ligand. So it will not force these electrons to get paired. Okay, so the reason this orbitals, the d orbitals, will not participate in the bonding, and then what you get is sp3 hybrid orbitals, 4 sp3 hybrid orbitals. So what you get is NiCl4, right? Is what you get is the sp3 hybrid is NiCl4 2 minus. Okay, the shape is tetrahedral, because it's sp3 is sp3 hybridization. What you get is a tetrahedral shape. What you get is tetrahedral here, and this is a, since there are, and this sp3 hybrid orbitals, for these sp3 hybrid orbitals, the electrons from chlorine, the 4Cl minus, will donate the 4 electron pairs. See, the minus charge, always remember the Cl minus, the negative charge means 2 electrons. Negative charge means 2 electrons. So it can donate 2 electrons to the vacant orbital. So that's what happens, and then you get sp3 hybridization and tetrahedral shape, and it's paramagnetic, and you have the, how many unpaired electrons? There are 2 unpaired electrons over there. So you can do the magnetic moment. So that is square root of n into n plus 2. That is square root of 2 into 2 plus 2. Okay, right. So you get root 8, and then that's about 2.82 Bohr magnetons. Okay, 2. So root 8 value I'll write over here. Root 8 is 2.82 Bohr magnetons. This is how you can give the answer in the case of NiCl for 2 minus. This is the discussion about this. And I hope you would have written this. And now, if I consider nickel cyanide NiCN4 2 minus, so here also I get the nickel 2 plus. So I get the 3D8 or a 0 type configuration, no doubt about that. And now you see what happens is Cn minus is a strong field ligand, and then it will force pair the electrons, in the orbital. So this is the concept what you need to get. So here you go. So it turns out to be like So this is the d orbitals. And now I will draw the initial condition. The initial condition will be like this. And now this is the 3d8 configuration. But because this, I told you this nickel 2 plus is subjected to a strong field like Cn minus. So what it does is this electron over here will just jumps back to here and creating one vacant d orbital, and you have one 4s orbital, and you have two 4p orbitals. Okay. So now this d, yes, 2p, right? So you get dsp2 hybrids you get, that is 4 dsp2 hybrids. 4 ds beta hybrid is what you get. And now you get a square planar structure. Square planar structure will look like this. Cn, Cn, Cn. This is a square planar structure. Is what you get for this NiCN42 minus ions. So the hybridization is dsp2, and 4 dsp2 hybrid orbitals will be formed. And now here this entire set, and what I'm drawing over here, this will create this dsp2, and here the electrons will be donated by the cyanide ion. So I am putting an into mark for the donated electrons from Cn minus. So this into marks refers to the Cn minus have donated, each Cn minus have donated 2 electrons. So that I am showing with the into marks. So that's how you get, and then there is no unpaired electron. So you have 0 unpaired electron. So magnetic moment is 0, and it's diamagnetic in nature. It's diamagnetic. So these are the things what you have to know about the NiCN42 minus. So this is a little bit explanation what I can give you, and afterwards you can write in your own words. Now let's move on to the next question. What is the formula of the compound in which the element Y, forms a CCP lattice, and the atoms of X, and the atoms of X will occupy, and the atoms of X will occupy two-thirds of tetrahedral voids. So, so in this question, it is given that Y forms a CCP lattice. So see that Y forms CCP. So if Y forms CCP, then the number of atoms of Y, so if I write NY, how many atoms will be there? 4 atoms per unit cell. 4 atoms per unit cell. That's what the CCP case is. Always you have 4 atoms per unit cell. And now you have the next one is that the atoms of X will occupy two-thirds of tetrahedral voids. So in CCP structure, when you have a CCP structure, there will be 4 octahedral voids and 8 tetrahedral voids. This funda you have to remember. This funda you have to write and remember. There will be, if you have a CCP, there is 4 atoms per unit cell, 4 octahedral voids. The number of octahedral voids is equal to the number of atoms per unit cell. This is what another thing, another way you can remember. So the exact thing is like 4 atoms per unit cell, that's 4 octahedral voids, and 8 tetrahedral voids is what you have. And now you have what you need to do is that, so already you have the Y atoms. Y atoms are 4 are available, and you have X atoms is what you need to count. X atoms are available in tetrahedral voids, but they occupy two-thirds of the tetrahedral voids, that is two-thirds of 8 is what they do by X atoms. So when we take the ratio N of Y is to N of X, or N of X is to N of Y, if you write that, so it becomes 4 is to 8 to 16 by 3, right? 16 by 3, this you can do. So 4 ones, 4 fours, you can try. So it's like 1 is to 4 by 3. When we multiply this with 3, I get 3 is to 4. So the formula of the compound is Y3X4, or you can write X4 by 3. So that's the formula of the compound. So this is how you can deduce the formula of the compound by using this fundamental idea. Okay, so that's the answer. The next question, let's move on to the next one. So the next one is a compound is formed. A compound is formed. A compound is formed by two elements. X and Y. X and Y. Atoms of element Y. Atoms of element Y as anions. Make CCP, and those elements of X and those elements of X, that is cations, X is cations, occupy all octahedral voids. What is the formula of the compound? What is the formula of compound? So this is the question. This is a very simple type, like what we did just before. So it is said that Y are the anions. The anions, they are forming, they represent the CCP structure. So Z is N of Y, that is 4. The anions are 4. Similarly, the cations, that is X, that is the cations, they are occupying all the octahedral voids, that is N of Y. So as I told you that N of X, sorry, in this case N of X. So here the N of Y, that the anions, they are occupying the CCP structure. In the CCP, the cations, they are occupying octahedral voids. Octahedral voids is equal to number of atoms in the unit cell, so that is equal to 4 once again. So if you consider the ratio like n of x is to n of y, so it's like 4:4, that is 1:1. So the formula of the compound is simply xy. So that's the formula. The formula of compound is nothing but xy. So hence the answer. So let's move on to the next question. So I'm answering some choice questions also. That's why the same kind of question may be repeating. So here we go. The next one is 45 grams of ethylene glycol. Ethylene glycol. That is given by the formula CH2OH. Ethylene glycol is mixed with 600 grams of water. So it's mixed with 600 grams of water. Calculate the freezing point of the solution. Freezing point of the solution. Calculate the freezing point of the solution given kf of water. kf of water is about 1.86 Kelvin kg mole inverse. So this is what the given. And now how to do this is we have the formula for the depression of the freezing point, that is delta Tf is equal to Kf times the molality. This is how we can use. And now that Kf value, we know that 1.86 Kelvin kg mole inverse. And now this is molality is 45 weight of the substance divided by gram molecular weight is about 62 gram mole inverse. That's how the gram molecular weight into 1000 by mass of the solution in grams. So that is about 600 grams. This is how you can substitute, give the substitutions. So after that you get the delta Tf. So once you calculate the delta Tf, that works out to be 2.25 Kelvin. So 2.25 Kelvin once you give the calculations. And now, so we know that Tf naught minus Tf is about 2.25 Kelvin. And now what is the freezing point of water? We know that very well. That is about 273. So Tf we can calculate, that is 273 Kelvin minus 2.25 Kelvin. So the freezing point drops down to about 270.25 Kelvin. 270.25 Kelvin. So that's how you can calculate. And okay, to have the idea of what we have calculated, okay, please note it up to here. I will give you the molality equation. Okay, you can pause the video and take it, and then molality equation is given by weight of the substance divided by gram molecular weight of the substance, that is gram mole inverse, into 1000 divided by weight of the substance, weight of the solution in grams. Okay, weight of the solution in grams. So this is how, in fact, that's weight of the solvent in grams or weight of the solution in grams. So depending upon the context, you can use. So this is, let's move on to the next question. So next question goes like this: for a chemical reaction, for a chemical reaction, R goes to P. For a chemical reaction, R goes to P. For a chemical reaction, R goes to P. The variation of R, that is concentration, versus time t is given by the plot. So you can see the plot I'm drawing there. Now it's given like this. Okay. And now this is the concentration R. This is versus time. This is the graph which is given. So the point 1 is that predict the order of reaction. The second one is slope of the curve. What does the slope of the curve give? Okay, slope of the curve, what does it give? Does it give? So please note down the question. I'll give the answer. So here is actually it's touching here. It's touching here. So it's evident that if this is a straight line with the R versus T curve, a straight line with a constant slope, which means it's a zero order reaction. Zero order reaction. The first part answer is the zero order reaction, and second part, the slope will give the negative of the rate constant. Okay, slope of the line will give negative of the rate constant. So the reaction is of zero order. The second part is slope of the line will give the negative of the rate constant. Okay, so that's what the answer is. Now let's move on to the next question. Another question: why acetic acid is more acidic than phenol? So in case of acetic acid, what happens is, first of all, it's an acid. And now when you draw the resonance structures, we end up with something called the equivalent structures. Okay, the charge will shift. The negative charge is shifting on oxygens only. That is called equivalent structure. Resonance structures will generate equivalent structures. So since they generate equivalent structure, so because the charge is shifting only on the oxygens, okay, so it generates an equivalent structure. So the reason the conjugate base, that means this is the acid, CH2COOH, if you consider this the acid, The conjugate base is something which, when you remove the proton, what you get, that is the acetate anion. This is UO minus. So that is stabilized. Okay, that is stable. The conjugate base is very stable. So in the case of phenol, when we start dropping the resonance structures for phenoxide anion, so you get a scenario of this kind. So here the charge shifting is happening between the carbon and oxygen. The resonance structures are not equal. Okay, resonance structures are not equal. For the conjugate base of phenol. Okay, but whereas the conjugate base of acetic acid, the resonance structures are equal. So this is the reason why. So we can write. So the reason why acetic acid is more stronger than phenol. The actual way is to check the pK values. pK values is the other one which you can check. pK values lower the pK, stronger the acid is. Stronger the acid is. So I can check the pK values. pK of, you can also write that the pK of acetic acid is smaller than the pK of phenol. Okay. So you can check this in the database. So hence acetic acid is more stronger. So this is the explanation one can do. Next one. Next question. Acidity of phenol is due to dash is given. The answer goes like this. It's a stability of phenoxide anion due to resonance. The resonance structures you can draw like this, the phenoxide resonance structures. So this is, you need some practice to do this. Otherwise it will be tough. So you can see the structures of the phenoxide, what I'm drawing over here. These are the resonance structures, and again comes back. So this is how one can draw the resonance structures and show the resonance of the phenoxide anion. Because of these resonance, it is stabilized. Okay. So since the phenoxide anion is stabilized because of resonance, that's why it shows some acidity. Okay. So this is the reason. So let's move on to the next one. Now arrange the following. Arrange the following in the increasing order of acidity. So you have this one given. COH. The second one is phenol, and third one is this one. So these are the things which is given. And now here you go. This is already an acid group. So, and next one is that the COH is an electron withdrawing group which increases the acidity of the phenols. And already acid is present. So this will be the highest one. So let's write this at the highest. Okay. This is nothing but salicylic acid. Okay. Salicylic acid. This will be definitely greater than one out of these two we have to see. The electron releasing groups will decrease the acidity of the phenol compared to that of phenol. So this is electron releasing groups decrease the acidity of phenol. Acidity of phenol. Okay, this is the one you have to remember. And electron withdrawing groups increase acidity of phenol. Acidity of phenol. So here you go, the phenol will be here. Okay, the phenol is much stronger acid compared to that of it's more acidic, I should say, more acidic compared to that of this one. So this is nothing but orthocresol, and this is phenol, and this one is salicylic acid. And this one is salicylic acid. So hence the answer. And then the next one, the next question. So what happens with this reaction? Predict the product of the reaction. So the phenol on treatment with Na2Cr2O7, H2SO4, H2O. When you take this, so you get something called phenols. Okay. Phenols. Okay. This called like phenol. Now, hopefully you have noted this one. Let's move on to the next question. Write the products of the following. Write the products of the following. So here we go. CH3COH on treatment with Br2 red phosphorus. Yes, CH2Br QOH. So that's the product what you have. The next one is the A. This is the B part of the question. CH3 CHO, that is acetaldehyde. Acetaldehyde is treated with LiLH4. These are reducing agents, so you get CH3 CH2 OH. So that's the answer. And the third one is that this is acetone. A strong treatment with zinc amalgam HCl. This is called Clemmensen reduction. Clemmensen reduction, the CO will go and then CH2 will come. So the answer is CH3, CH2, CH3. In Clemmensen reduction, what happens is that the C double bond O is converted to CH2. Okay, CH2 group. So that happens in the presence of zinc amalgam HCl. Zinc amalgam plus HCl combination, this thing will happen. So these are the reactions. Now, next question. Please note it. You can pause the video and note it. Next question is write the chemical test to distinguish between propanol and propanone. Propanol and propanone. So the case is propanol. How does this propanol looks like? So first let us see CH3, CH2, CHO. This is how it looks like. This is propanol for us. And the propanone is nothing but acetone. So here the trick is that when you have COCH group, you can use iodoform test. Iodoform test to distinguish. If you have COCH group, you can distinguish that. If you are given propanol, definitely it is having COCH3. This you can treat this with sodium hydroxide and I2. This is the test you can write. So you get iodoform CHI3 followed by CH3 CONA, and here you don't have COCH group. So when you use I2 NaOH, you have no reaction. Okay. So this is how you can distinguish this. The next one is how to distinguish the benzoic acid and benzaldehyde. So what you can do is that two kinds of tests are there. So if you take benzoic acid and treat it with by the way, how the benzoic acid looks like this. So over the benzene you have COH group. That's how benzoic acid looks like. And then when you treat this with NaHCO3, this is the test one. So you have the CO2 evolution will happen with effervescence, and now followed by this CONA. Okay, sodium salt of benzoic acid, sodium benzoate plus water. So this will give bubbles. That's way you can test it. And benzoic acid plus NaHCO3 is the test you can follow. The next one is that this benzaldehyde when you take plus NaHCO3, no reaction. Okay, this is how you can distinguish. This is the method one of distinguishing. The method two is by method two is like treatment with treatment with ammonical silver nitrate, ammonical silver nitrate solution, silver nitrate solution. You can say tolerance test, or silver mirror test, silver mirror test. Benzaldehyde gives this. Benzaldehyde gives this test, gives positive result, forming silver mirror, and the benzoic acid fails in that. Benzoic acid fails in that. Fails, no reaction. So this is how one can distinguish benzoic acid and benzaldehyde. This one. So this is how one can distinguish. So actually what happens with the silver mirror test is that benzaldehyde will undergo oxidation in the presence of this ammonium silver nitrate solution. So what you get is benzoic acid. And here, when you already have the benzoic acid, further it will not get upstaged in the solution. That means the silver get reduced during this process and the benzaldehyde will get upstaged. So this is what happens and then forms the silver mirror. So this is the ideas what you need to have in mind. The next one, write the structures. Write the structures A, B, C, D. Write the structures A, B, C, D in the following reaction sequence. In the following reaction sequence. So write the structures of ABCD in the following reaction sequence. Given CH3 COCl H2 palladium BaSO4 produce A and value NaOH and produce B, and then after heating it gives C, and then A you have CH3 MgBr and then followed by H2O plus, and then the product is C. You got to write the products ABCD. So I'll try this. This is very simple. H2 palladium BaSO4. You will get the corresponding. This is acyl chlorides. H2 palladium BaSO4. You will get the corresponding aldehydes. So I'll write what is A. A is our acetaldehyde, and A is treated with dilute NaOH. So you have this dilute NaOH. When you treat this with dilute NaOH, it will undergo aldol condensation reaction. So This is what you get. This is what you got. And now this is our B. And then B on treatment, B on heating, it will give the corresponding alpha beta unsaturated aldehydes. So this is what you get. This is called protonaldehyde. Okay, this is our C. And in fact, A is treated with CH3 MgBr and then H2O plus. So it will give CH3 minus ion. This will go and hit here. MgBr will get attached to the oxygen. So here what you get is CH3, COH, CH3. Yeah, that's what you have. So these are the compounds what you have, and these are the required reactions. So this is our B. The product number, product B is this. And product A is coming from CH3COCl. This is on treatment with palladium BaSO4. Okay. So when you do this, this is the reactions what you will have to know. Now the next question. Okay, hopefully you would have noted. Pause the video and then make a note. We'll go to the next one. The next reaction is CH3C double bond O CH3, and then zinc amalgam HCl. This is given. So what you get here is this Clemmensen reduction I just told you earlier. So what you get is this one. Instead of C double bond O, you get CH2 group over here in the presence of zinc amalgam HCl. The next reaction is that when this is called HVZ reaction is what they have given. CH3COH. So when you treat this with Br2 red phosphorus, you are going to get at the at this carbon adjacent to the carbon adjacent to this is called alpha carbon. At the alpha carbon, you will get the bromination. So you get CH2 Br COH. So this is what happens. This is called HPZ reaction. Okay. Now, hopefully you would have written. Next question. Why sulfur exhibits paramagnetic behavior, in vapor state. So this is the question. So what happens is in vapor state, sulfur partly exhibits as S2 molecule. Partly exhibits S2 state or exists, you can say exists as S2 molecule. Okay, partly. It exhibits S2 structure like O2. Okay, like O2. Like O2 molecule. So it has unpaired electrons in 5-star anti-bonding orbitals. Anti-bonding orbitals. Hence the vapor state. Hence the vapor state. Hence the vapor state of sulfur exhibits paramagnetism. Exhibits paramagnetism. So please note. So hopefully you have noted. You can pause the video and note. Next, fill up the reactions. CaF2 plus H2SO4. Fill in the blanks type of questions. CaF2 plus H2SO4. That will give HF plus CaSO4. This is the answer. The second one. So what happens when SO3 passes through water? So SO3 plus H2O that gives H2SO4 first. H2SO4 means. So further, when you pass this H2SO4 plus SO3, it further when it is passed, you will get H2S2O7, which is volume. So this is what you have to keep in mind. These are the reactions. Okay, now let's move on. So they are now assertion reason type questions. Assertion. Amines are basic in nature. Basic in nature. This is a true statement. And are they writing it as amines have lone pair electrons. Amines have lone pair electrons. Lone pair of electrons on nitrogen atom. Nitrogen atom. This is also true. And we can say R is correct explanation. Correct explanation of E. So that's the answer. Assertion reason type questions we are dealing now. So you can say both are true. Both A and R are true. Let's see the next one. Next one is molecular mass. Molecular mass of acetic acid. Molecular mass of acetic acid in benzene. Benzene is 120 instead of 60. Instead of 60. The reason they're writing it as the carboxylic acids. the carboxylic acids, exist as dimers, exist as in fact cyclic dimers. So I'll write this separately, that's better. So the assertion, this is a little bit longer, so I'll rewrite that. In molecular mass of assertion is molecular mass of acetic acid is 120 instead of 16 in benzene. That's the assertion. The reason is they have given that the carboxylic acids exist as cyclic dimers in which the two molecules of acid, are held together by strong hydrogen bonds. So this is true, and this is also a true statement, and R correctly explains A. So this is the answer. Both are true statements. R correctly explains A. Now this point I will take the break. Part 3 of the question paper will come next. So this is the part 2, and then I will give the part 3 very soon. And I feel like I will give like the part maybe I have to make like 5 parts of this question paper. Maybe I have to make 5 parts. Okay, I will join everything as a video and then I'll plug into the same and try that, or otherwise I will release it as two or three different parts. Anyway, thanks for watching the video. Like the video, please give a like and subscribe. Thank you all. So, friends, this is the part 3 of the question paper. So, the assertion and reasons of the chemistry question paper. Bond angle in H2S is smaller than H2O. So okay. So the reason what's given is that electronegativity of central atom increases bond angle decreases. So this one, the bond angle in H2S is smaller than that of H2O. That is, A is true statement, and this is false statement. So here the reason is that if you see the water and H2S both are having the similar sort of structures, and then the oxygen, this having high electronegativity pulls the electrons towards it, and hence the repulsion between these two will increase, and which increases the bond angle thereby. And now, when in the case of sulfur, it's not that electronegative compared to that of oxygen. So the lone pairs are little bit away in this case, so the bond angle reduces to almost 90 degrees. Okay, so this is about 107 degrees, right? In the case of water. So so the so this is the reason why. So the electronegativity increases on central atom bond angle increases. So hence this is how you can give the answer to the question. Okay. Now let's move on to the next question. Next is the question. The assertion is the molarity of a solution. Molarity of a solution in a liquid state. In liquid state changes with temperature. This is a true statement. And now the reason what they have written was volume of the solution. Volume of the solution changes with temperature. Changes with temperature. So this is what is given. This is also a true statement. Okay. So hence the A and R are true, and then the R explains. That's the reason. R explains the A. So because you know that molarity is the number of moles per liter of solution. So here the volume term is coming. So since the volume changes with temperature, molarity changes with temperature. So that's how you can answer this question. So let's move on to the next one. You can pause the video and then make a note of these things. Okay, fine. So R is the correct explanation of E. That's what you can see. Now the another one is the passage questions. The passage questions that in the section A. So that contains these questions. Okay. Coagulating power of the ions Na plus, Ba2 plus, and Al3 plus follow the order. So that's what is asked. Follow the order. Which order do they follow? So as the charge increases, the coagulating power increases. So simply you can write Na plus less than, Ba2 plus less than, Al3 plus. So that's all you can say. The valency will decide the coagulating power. Next one. The next one, what was asked is out of KCl, KNO3, and K2SO4, and K4FeCN6, and K4FeCN6. Okay, all these things which are given to us. Now, which are the following is most effective? Which one is most effective which one is most effective for most effective in in causing coagulation of ferric hydroxide soap, of ferric hydroxide soap. So it's easy to tell that it's K4FeCN6. That's the answer for this question. So under the same token, you have K4FeCN6, FeCN6 4 minus. So is the ion what we have. So that has the highest negative charge among all the among all the other things. So that has the best coagulating power. That's how you can answer. Now let's move on. So this is based on the K4 FeCN6. The answer is based on you when it dissociates, what you get is 4K plus and your FeCN6 4 minus. This is what you get. And now according to Hardy Hardy's choose rule. Okay. The greater the valency, the greater the valency of the fluctuating agent, or you can say ion, the greater the ability, to bring about coagulation, So the next one more point I give you, the ability of an ion to bring about coagulation, of a given colloid There's an important point I'm just mentioning. We have already answered the question, but I'm just giving some important points for you. Given colloid depends upon both the magnitude and the sign of the charge. And the sign of the charge. Ions of opposite charge. Ions of opposite charge and larger magnitude bring about coagulation even with smaller amount, even with smaller amount, even with smaller amount. So this is the idea what you need to have. So based on this point, next question will be coming. So I can make a note of this part in the video, and next we'll be moving to that. The question is that higher the coagulating power, higher the coagulating power of the ion dash will be its coagulating value. Will be its coagulating value. So here, just now the point, so amount what we take is less, that means that's the coagulating value. So coagulation power is inversely proportional to coagulation value. So this is what you need to keep in mind. Coagulation value is the amount of substance what you take, or you can say that's population value. Smaller the coagulation value of the electrolyte, coagulation value of the electrolyte, larger is its coagulating power. Larger is its coagulating power. Or frustrating power. Larger is frustrating power. This is how you can see. So these are the ideas what you need to have. The next part is in the question paper, we have MCQs. The MCQs are coming, multiple choice questions. So the first one is in spotty defect. Option 1, density of crystal increases. Option B, density of crystal decreases. Option C is density of crystal remains unchanged. Density of crystal remains unchanged, and the option D is none. So it's the density of the crystal decreases when you have the spotty defect. So So what is the spotted effect is like equal number of anions, and as well as cations will be missing. Okay, will be missing in the lattice. That's what the spotted effect is, missing the lattice. That's what the spotted effect is. So let's see the next question. So the next one. Now the second question, colligative properties. Colligative properties. Depend upon option A is nature of solute. Option B is number of solute particles. Number of solute particles. Number of solute particles in solution. Option C is about the physical properties of solute. Option 4 is none. Option B is the right answer. Number of solute particles. So that's the answer, and then let's move on to the third one. The correct decreasing order of basic strength. So the option A is ASH3 greater than SPH3 greater than PH3, that's greater than NH3. This is what is here. Option B. So they are touching the fifth group elements for us. So SPH3 greater than ASH3, that is greater than PH3. So that's greater than NH3. So we have that, and then C is about NH3, that is greater than PH3, that's greater than ASH3, that's greater than SPH3. So that's the C part, and C is the right answer. So down the group, this basic strength decreases. That's what happens in the case of hydrates. So that's one. So anyway, option D also for completeness I'm doing PH3 greater than ASH3, that is greater than SPH3, that's greater than NH3. So option C is the correct one. So down the group, the hydrate density increase. Okay. So that's the. So why the reason is that down the group, when you go the electron density on central atom will decrease. Okay. Central atom will come down. Okay. That's the reason. You can note. So hence the donating ability will decrease. Okay, tendency to donate. Hence, electron donating tendency will decrease. Tendency will decrease. So this is the reason. You can make a note. Yeah, you can pause the video and make a note. Let's move on to the next one. So next one, which of the following, which of the following has maximum number of unpaired electrons, maximum number of unpaired electrons, that's what is given. So that's first one is titanium 3 plus. So option B is iron 3 plus, and option C is chromium 0, and option D is copper plus. So this you can obtain by writing the electron configuration. So copper 0 is what? So the titanium 3 plus, if you write the configuration, that will be about 3D1. And iron 3 plus, if you write the configuration of iron 3 plus, you get 3D5. Okay. And for the 0, that's, don't forget this one. And the chromium 0, you will have 3D5 and 4 this one. So here you have the maximum number of unpaired electrons, and then copper plus you have the 3D10 configuration, completely unpaired electrons. So chromium 0, you have 6 unpaired electrons. Okay, 6 unpaired electrons is there in the case of chromium 0. So the reason you can check down with the electron configurations of this one. So option C is the right answer. So let's move on to the next one. So pick one. So which of the following is most likely the structure of CrCl3 6H2O, CrCl3 6H2O. If one third of total chlorine, one third of total chlorine of the compound is precipitated by adding AgN, one third of the compound means you have 3 chlorines. One third means 1 chlorine is precipitate, means 1 chlorine is outside. So the answer would be, we can predict the answer. So the answer is, as for the options, I can write CrCl3. They have given CrCl3 6H2O. That's the first option. Second option is that CrH2O, okay, tries Cl3. This is what is given, and then outside H2O. So that's C is like CrCl2H2O. That's what is given. So ClH2O. So this one is option C. Why? Because the reason this chlorine is outside the coordination sphere, this can be ionized, and this chlorine can be precipitated. This happens to be one third of the chlorines what is given as per the question. So option C is the right answer, and option D what they have given is CrClH2O. So this is what is given. I'm writing for completion's sake. So Cl2H2O. So if this is the answer, then it will be 2/3 actually can be precipitated, and this cannot be the case. So because they have not mentioned which is the valency, which is ionizable valency, which is the secondary valency, they have not told anything about that. So whereas here interchlorines are inside this one, this coordination sphere, and the rest of the cases it's shifting all over. So here H2O 4 times is what is given. So that's the answer. You have option C is the right answer. And now let's move on to the next one. So the next one is the best method of converting an alcohol to an alkyl halide. An alkyl halide. An alkyl halide. So the best method of converting an alcohol to alkyl halide is so the options are given. A is PCl5. Option B is dry HCl. Plus anhydrous AlCl3. So the option C is SOCl2-pyridine. SOCl2-pyridine. Option D is all the above. So this is the option given. So SOCl2-pyridine is the best option. The reason being it will produce gaseous products after conversion of alcohol to alkyl halide. Gaseous products are SO2 and HCl. Gases will form. So since they are byproducts and if any traces of HCl is there, pyridine will trap it. So the reason option C is the right answer. So let's move on to the next one. So the next one is IUPAC name of CH3 CHCl CH2 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 CHOH CH3. This is what you have, and then we have to give the IUPAC. So the chlorine is preferred. So we see 1, 2, 3, 4, 5, 6. So the 2-chlorohexane 1-ol. 2-chlorohexane 1-ol. Sorry, 5-ol. So you can give 5-ol. And the fifth position OH group is there, so 5-ol. So that's how you can give the answer. 2-chlorohexane 5-ol. Chlorohexane 5-ol. That's the answer. What you get. So let's see the next one. And now the correct order of necessity of the following. The next one. Correct order of necessity of the following. So of the following is given that this is the first one is aniline. So the next one is the para-nitro. And the nitro group at the para position, then this one. This one. So these are A, B, and C. So this follows the order. If the nitro group is there, deactivating groups will reduce the density of the aniline systems, kind of things. So you have this one non-aromatic amines. They are highly basic. So you can see C greater than A greater than B. This is the order it follows. Or in the if it is the increasing, or if it is the this is the decreasing order, the increasing order wise B less than A less than C. This is the order of density. This is the increasing order, and this is the decreasing order. This is the decreasing order. So depending upon the answers, you can give whatever. So this is the decreasing order. So the next question. Let's go to the next one. So here we go. The nucleic acids. Nucleic acids are polymers of dash. That is nucleotides. Nucleic acids are the polymers of nucleotides. So that's what the answer is. So next one. So next, the next set of questions will follow. Now the next question is explain the terms. Explain the terms. There's the next question. That is the part one is ambidentate ligand. Ambidentate ligand. And part B is that denticity of a ligand. Denticity of the ligand. And option, the third part is the crystal field splitting. Crystal field splitting in an octahedral complex. So these are the things what are given. So we'll answer one by one. What is ambidentate ligand, and then denticity of a ligand, and crystal field splitting in an octahedral complex. So the first part is ambidentate ligand. What's an ambidentate ligand? Ambidentate ligand is like ligands which can bond. Ligands which can bond. Ligands which can bond to the central atom. To the central atom. Central atom. Ligands which can bond to the central atom in two places. In two places. Or you can say that two atoms can act as donors of electrons in the same ligand. And the another thing is that only one can act at a time. Only one atom can bond at a time. So that's the another thing. So for example, you can so we can have two atoms two different atoms, I can say two different atoms. So two places, two different atoms can act as donors of electrons. Okay. So you can say that the atoms of different elements. Okay. Atoms of different elements. Okay. Within the same molecule. Within the same molecule can act as donors. So one at a time. So one at a time. So this is how you can give the explanation. You can pause the video and note it down. So the ambient ligands examples are like cyanide. Okay. So either carbon and nitrogen, thiocyanide is Cn minus. Okay. The sulfur or nitrogen, one of the things can bond. So another one is nitro NO2 minus. So either it can be from nitrogen or it can be from oxygen. So these are some of the examples of ambient ligands. The next one is about, let us talk about the denticity of a ligand. Denticity of ligands. So here the denticity is about number of donor atoms or groups. Okay. In a single ligand, that can bind the central metal, that can bind the central metal atom, can bind the central metal atom at a time, you can say, in a coordination complex. So they are like monodentate, bidentate, tridentate, like that. The ligands will be there. So when you consider monodentate, the monodentate category is like the cyanide minus. So this is one atom at a time it can do. So that's the reason. And O2 minus. Though they are ambidentate, these are monodentate. Okay. Now they can do only one atom at a time. Okay. Only one atom can donate at a time. So that is the thing you have to understand. And now if you take a bidentate is like when you have the ethylene diamine, okay, the ethylene diamine for you, and then you have, this is the oxalate. This is the oxalate anion. Okay. These are the examples of bidentate ligands. These are the examples of bidentate ligands. And so on, you can have up to hexadentate ligands. Okay. Hexadentate ligands are like EPT. ఇంటి తల్లి ఇలా చేసావు. Oh. Hexadentate ligands are like EPTA. So sorry friends, I had a problem in between, so resuming the record. So this hexadentate are like EBDA kind of ligands you will have. So let's see the next one. Next question we have is that the octahedral splitting. Okay, octahedral splitting. What happens in the octahedral splitting? I will tell you few points. Like the first part is ligands approach along axis, along the axis. Okay, the dx square minus y square and dz square will be repelled more and forms EG set, and dxy, dyz, dzx will suffer less repulsions, forms T2G set. So these are the basic things you have to write, and then the field splitting. So here, if you take the EG set, electron goes to T2G set, stabilized by 0.4 delta naught, and if electron goes to EG set, EG is destabilized by 0.6 delta naught. These are the main points you can write. So, and then the splitting in the octahedral field you can represent. So there's a 5 orbitals. Initially they are degenerate, and then slightly they will be lifted in the energy, and then you have this one, and then they will get split into 2 orbitals. The orbitals along the axis, this is dx square minus y square and dz square, they repelled more because ligands should approach from the axis. And now this is like you have 0.6 delta naught, that the destabilization, and then you have this one, and here you have the EG set. This is EG set, and then you have the T2G set. For further, you can refer to your textbooks. So this is the T2G set, and you have dxy, dyz, dzx. These are the things, and then this is what you can represent, and this is Barry center. Okay. And then you have the Barry center. I'm just checking whether anything I missed. I don't think I have missed anything. Barry center. So another thing is that if the pairing energy is more than that of delta naught, the first electron, say we can say the fourth electron goes to EG. Fourth electron goes to, so this pairing energy more than that of delta naught, fourth electron goes to EG. So that's what happens. That is one point. The other point is that if the pairing energy is less than that of delta naught, fourth electron goes to T2G. So these are the points what you have to keep in mind while writing the octahedral spin splitting. So here we go. Next one. So let's see the next one. We have So the first one, why aniline does not undergo Friedel-Crafts reaction. Friedel-Crafts reaction. So that's the question. So you can answer this by saying this aniline. You can show this reaction aniline plus AlCl3. It forms a salt. It forms a salt. Okay, this is the salt formation. Salt formation with AlCl3. Aniline forms a salt with AlCl3. And this salt is here. This NH3 group is electron withdrawing type, electron withdrawing group. This, so hence because it is electron withdrawing, the electron withdrawing groups does not favor the Friedel-Crafts reaction. So that's how you can give the answer. And then because the formation of the salt, this salt formation does not favor FCR. So because it is this group, what is formed is electron withdrawing nature. This is how you can account for this. Now let's move on to the next question. You know, ethylamine is soluble in water. Aniline is not soluble. Not soluble in H2O. So we need to explain this. So you can say that ethylamine, that C2H5 NH2, it can forms strong hydrogen bonds with water as C2H5 NH2 shows this C2H5 group. I can say C2H5 ethyl group shows plus I effect and it increases electron density on nitrogen atom, which favors hydrogen bonding. So which favors hydrogen bonding. And the next one is that when you have the other one, in case of aniline, and you consider the aniline case, the electron density is taken up by the benzene ring itself. So because of the formation of resonance structures. So the availability of the electron is naturally less in the case of aniline for hydrogen bonding. The polarity of nitrogen is also reduced because of this. So the electron density is lesser. You can say electron density is lesser in case of aniline. Okay, that's one thing. And then the next one is that this group, the benzene, the phenyl ring being hydrophobic. Okay. Does not allow allow the hydrogen bonding to form properly. So these are the reasons you can account, like and so you can say that ethylamine is soluble in water and the amine is almost like insoluble in water. So the one reason is the delocalization of the electron. Okay, this is the one, resonance electron delocalization. These are the facts you can give in the answer. So that will close and then we go. So the next one is that the next one. Okay, we will see the next question. State Hvac law of independent migration of ions. Of independent migration of ions. So that's the first one. Why does conductivity of solution decreases with dilution? So that's what we have to answer. So the answer is that the limiting molar conductivity of an electrolyte can be represented as sum of individual contributions of its cations and anions. The conductivity of a solution decreases with the dilution as less ions are present for conduction. As less ions are present for conduction. So that's the answer you can give. Now let's move on to the next one. So calculate delta GR naught of n log k to the base e, or sorry, log kc is what they asked. Log kc per the reaction for this unit. For the reaction 2Cr solid plus 3Cv2 plus aqueous gives 2Cr3 plus aqueous plus 3Cv solid. So what is given is that given that E naught of cell, they have given it as like plus 0.34 joules and 1 farad is 96,500 coulomb mole inverse. Is what is given, and then we have to find delta G of the reaction, delta G naught of the reaction, and delta G naught of reaction is minus NFE naught. You can write this. So the N is the number of electrons transferred, and you can see that easily that N is 6 electrons are being transferred, because you see this chromium is going to chromium plus each chromium is using 3 electrons, 2 chromium, 2 into 3, 6 electrons. So the cadmium, you can see that 3 cadmiums, each cadmium is 2 plus, so 6 plus charge to neutralize the cadmium. So 6 electron transfer reaction is what is happening. So you can plug in that 6 is N minus 6 into 96,500 and E naught is 0.32. So when you substitute the things and then you can work out the answer. That answer happens to be 1 negative 196.86 kilojoule mole inverse. So this is what you get first. And we know that we also know that the delta G is negative negative ln, sorry, that is negative minus RT ln K. This, we know this very well. And when you plug in the things, so the ln Kc, okay, we'll work this out later. So we have delta G naught of R is negative 2.303 RT ln Kc, logarithm of Kc. You convert, and then log Kc is what they asked us. Log Kc is minus delta G naught of R whole divided by 2.303 RT. So substituting the values, what we get is about 34.5762 is the value you get for log Kc. So that's the value you are going to get. Or you can use this equation very well, that you can use this equation very well, that E naught of cell is equal to 0.0591 divided by N log Kc. This also you can use. You know the E naught of cell, that is 0.34, that is equal to 0.0591 whole divided by the value of N is 6. So that's log Kc. So you can use a log Kc value is 6 into 0.34 whole divided by 0.0591. So this way also you can calculate, you get 34.5762 around. So this is the value we're going to obtain. The next question is that calculate EMF of the following cell at 298 Kelvin. So that's what we have to do. So here you see 2Cr3 plus 2Cr solid, sorry, 2Cr solid plus 3Fe2 plus, that's about 0.1 molar, and that gives 2Cr3 plus. Chromium is getting oxidized, so that forms the anode. So the next one is the 3Fe solid. Iron getting reduced, that forms the cathode for you. And the E0 value of the Cr3 plus chromium, the reduction potentials are given here, minus 0.74 volts, and the E0 value of iron 2 plus to iron, so that is 0.44 volts. These are the things which are given to us, and then using this information, we have to find what is the E of the cell. So here we go. The first thing is to find the E0, E0 of the cell, that is E cathode minus E0, E0 of cathode minus E0 of anode. We understood that the cathode is the iron, and the anode is that of the chromium. So we get minus 0.44 plus the anode part is, because negative of negative is positive, so you get 0.74. That's positive potential 0.30, 0.30 volt. So positive potential means this reaction do happens. So because delta G is equal to minus NF. And now you know that this is 6-electron transfer reaction, this reaction. So E0 of cell you have, and now we'll directly write the formula. E cell is equal to E0 of cell minus 0.0591 divided by the value of N is 6, and then log of, you can remember it as like oxidation with the concentration of oxidation species, that is whole square divided by the reduction whole square. So here the stoichiometric is like 2 you have in the reaction. So that's iron, we have iron, I think the reduction. Let's see the stoichiometry. So that is cube here. Okay, cube, the reduction whole cube is what we have to write over here. So as per the stoichiometric portion, this is how it works out, right? Fine. And now, so when you work out, so you get this about plug in the values, you get 0.32 volts is what you're going to get when you plug in the concentrations and do that. And now the oxidation species, if you look at the species which is getting the oxidized, okay, so that is oxidized species is 0.01, 0.01, that is concentration of the chromium 3 plus. This, the stoichiometric coefficient is 2, so this has to be squared. So that's how you get. And then the other species is the iron 2 plus, that you had to cube it because the stoichiometric coefficient is 3 over there, so it works out to be 0.1 whole cube. That's how you just plug in the things and then you get the things done. Okay, fine. Now plug in the terms, you get the answer. This is the only. Now after that, we have the next one. So the next one is the conductivity of 0.001 molar acetic acid is 4 into 10 to the power of minus 5 Simon meter inverse. Okay, calculate the dissociation constant. Calculate the dissociation constant of acetic acid
of acetic acid if lambda naught m for acetic acid acetic acid is 390 Simon centimeter square mole inverse. So that's the thing. So the answer, you can do this by finding the lambda, that is kappa into 1000 by the molarity. So you can do this by 4 into 10 to the power of minus 5 Simon centimeter inverse into the 1000 whole divided by, you have 0.001. That's the concentrations. So the molarity, everything is given. So lambda value, first we'll find lambda value, we'll find it as 40 Simon centimeter square millimeters. So this is the value you get. And given this lambda naught is also given to us. Lambda naught is 90.5. 90.5 Simon centimeter square millimeters. So this is what you have. From this, we can calculate the degree of dissociation. Alpha is lambda by lambda naught. Using this formula, you can calculate. The lambda is what we got is 40 divided by 390. Okay, 390.5. So that works out to be 0.102. That's the degree of dissociation we got, and then the K for the weak acids is given by K equal to C alpha square, and C is 0.001 into alpha square is 0.102 whole square. And now you get it around 1.04 into 10 to the power of minus 5. That's the dissociation constant of acetic acid, and this is the degree of dissociation. This is called degree of dissociation. This is the required dissociation constant. Required dissociation constant. So this is what you have. Next one. Let us see the next question is that we have the question, why ozone is thermally unstable. Thermally unstable. So this is what we have to discuss. Its reason is because that ozone goes to O2. This reaction is exothermic plus heat. Reaction is exothermic. Reaction is exothermic. Delta H value is negative. And you can see one more thing is that O2 plus O, it will form the entropy increases in this reaction. So when we calculate the delta G, that is delta H minus T delta S term, this entire thing is a negative quantity because delta S is entropy, that is delta S is positive, minus T delta S is a negative quantity, delta H is also a negative quantity. When we add up delta H minus T delta S is a negative quantity, you can see that delta G is a negative quantity. Delta G is negative means that reaction is spontaneous reaction, hence the reason this reaction is entropy favored, and then it is exothermic. So the reaction is a spontaneous process. Okay. So hence the reason that this ozone is thermally unstable. So thermal decomposition will happen. So this is the explanation you can do. And now the uh, fluorine, why fluorine forms only one oxo acid. Why fluorine forms only one oxo acid? So that is HOF. Why it is so? So you can account for small size of fluorine and high electronegativity of fluorine does not allow it to form central atom. These are the reasons you can give. Central atom for higher oxo acids. Okay. Higher oxo acids. So these are the reasons you can account for the fluorine cannot form the higher oxo acids. The next one is like draw the structures of BRF5 and XIF4 and XIF4. You can work out the hybridizations of BRF5 will form a pyramidal structure. BRF5 forms a pyramidal structure. So that's BRF5 for you. And the lone pair is here. And now XIF4. It's a square planar structure. And lone pairs here like this. So that's XIF4, square planar. This is pyramidal and square planar. And both will have the hybridization of sp3d2. So it's like sp3d2. Yes, of course, it's have hybridization of sp3d2. When you have sp3d2 hybridization, the lone pairs will reach the apex. So that is the idea. What you have. The next one is next one is why two more questions to do this paper. The stick why the acidic strength of these compounds increases in the following order. So it's pH3 less than H2S less than HCl. This is the order. So why it is so? So we have to answer this. So the acidity of a molecule depends upon the polarity polarity of the bond between central atom and hydrogen atom. Okay, this is the point number one you have to write. So you can pause the video, note it. Now the point number two, right over here. Point number two is greater the polarity, greater will be the acidity. Greater will be acidity. And third point is that polarity of the bond depends on electronegativity of the atom connected to hydrogen. Okay, these are the reasons what you can give. In the period, you can see that fluorine is greater than sulfur and greater than phosphorus in the electronegativity order. So this is the order of electronegativity you can write. So you can see the acidic strength will follow the order HCl greater than H2S greater than H3. This is across period. This is how you see the electronegativity order, and hence the greater the electronegativity, greater the acidity. That is the idea which is reflected here. And now the next part of the question is the last part. Why oxo acids of fluorine follow the order HCl4 greater than HClO3, that's greater than HClO2, that's greater than HCl. Why it is so? So the answer can be written as it's the oxidation state of fluorine which is deciding that. The point number one is acidity of oxo acids or acidic strength, you can say acidic strength of oxo acids of fluorine increases with increase in the oxidation number of fluorine. Okay. Increases with the oxidation number of fluorine. That's the first part. The second part of the answer, point number two, is the oxidation state of fluorine increases with increase in the number of oxygen atoms around fluorine. non-chlorine and oxo acids. Oxo acids. That's the next point. You can write. So this is the reason you get this HClO will be less than, hence you can say so HClO2 less than HClO3 less than HClO4. This is the order it will follow, and that's the end of the question paper for you. So if you have any queries, you can put up in the comment section, and then you can claim any doubts for there in the comment section. And thank you all for watching the video so patiently. And please note it, it should be really helpful for you for your board examinations class 4. Yeah, thank you all. Thank you. If you like the video, please do subscribe and hit a like. Thank you all.